We're going to talk about another method for solving ax equal to b. Typically not taught in a lot of linear algebra courses, but they're iterative methods. We've already talked about iterative methods early on. That iteration is one of the things that the computer is exceptionally good at, just putting things in a loop and progressing forward in sort of in a for loop or something of this nature. But we can exploit this in ax equal to b. And I'm going to show you a new way to solve ax equal to b that relies on iteration schemes. And this can be a powerful new method because we're going to use it quite a bit for solving large-scale systems, or it is used commonly to accelerate very large-scale ax equal to b problems. So let's talk about solving ax equal to b. Again, the focus here isn't so much on how to solve ax equal to b. The focus is on the actually algorithmic aspects of how we solve this ax equal to b. Okay? And so here's a 3x3 system of equations. 3 equations, 3 unknowns. Just wrote down some linear system of equations. And so normally what we might do is Gaussian elimination, which is the most expensive, or we might do an LU decomposition of the matrix to make this faster. But now what we're going to do is do something a little bit different, which is we're going to take this and we're going to make an iteration scheme out of it. So from the first equation, we're going to solve for x. From the second equation, solve for y. Third equation, solve for z. And this is what you get. So let me go back. Here are the equations. So if I solve for x in this one, right, I move the y and the z over to the other side, divide by 4. If I solve for y for this one, I move the x terms and the z terms over, divide by 8. And here I move everything over and divide by 5 to get the z isolated on the left. And these are the equations that you get. So I haven't really done anything. I haven't made any progress forward really in solving this. But now what I'm going to do is I'm just going to make up an iteration scheme. And here's how the iteration scheme is going to be. I'm going to go ahead and start with some guess for the x, y, z and throw it into the right hand side. So here we go. These are the right hand sides, and these are the yks, xk, z of k's. And I'm going to produce new values of x, y, z's, which are k plus 1 at the k plus 1 step. So I put in a guess, and using these equations, I produce new values of x, y, z. And then I just keep doing it. This is an iteration scheme, right? The kth value produces the k plus first, the k plus first produces the k plus 2, and so forth. So initially I might guess values of x, y, and z, and then just start to iterate and see what happens. Now here's what's interesting in doing this. We're going to guess initial values of x naught, y naught, z naught. We're going to iterate this, what's called a Jacobi scheme, which is I take my current values and I multiply, and essentially the matrix A is going to be determined by this thing here to get a new value, okay, of x at k plus 1. And then I ask the question, does this thing converge? So if I keep iterating, does x of k and x of k plus 1, do they shrink down below some tolerance? Let's say 10 to the minus 6. Okay, so I'm looking for a fixed point of the iteration scheme. And that would actually be the solution to my x equal to b. So, in fact, if I do this, here's what happens. I start off with a guess here. This guess is 1, 2, 2. That's my initial guess for x, y, and z. And I start iterating. And notice what happens. By the 15th iteration, I have the solution down to, 6 or 7 decimal places. By 19 iterations, I have the exact answer to numerical precision, 243. So all I did is set up an iteration scheme and started going, and it actually converged to the solution, which is an amazing result, right? It means I just started off with a guess, I let it iterate, and it gets to the solution. And the real question that comes from doing this is, how fast can I get a solution for this? But before we do that, let's just implement this. This is a very simple architecture to set up the iteration. And so here's a little Python code to help us out with it. So first of all, I make an array, NP array is 0. X and Y and Z are all zeros. So I start off, that's going to be my initial guess, is zeros. And in fact, in many algorithms that require a guess, often the guess that's provided, if you don't provide one, is 0, 0, 0. And so now what I'm going to do with this guess, I'm going to say, okay, let's do a for loop. So this is going to be my iteration. Remember, the iteration is going to be a for loop. And I'm going to produce new values of x, y, z, which is append x times, and here, by the way, is the calculation of the new value. The new value, new value. Remember, these are just these equations right here. Evaluating these equations And that's what these are right here. So I produce new values, and I append them to the old values, and I just keep in this loop. I keep appending new values, and I'm going to go through this loop 100 times unless I get out of there more quickly than 100 times. And how do I get out? Well, for instance, here I could just look at the x values. If I look at the x value, the new x value, and the old x value, if they're less than 10 minus 5, I have a break statement. So it's going to iterate until the x value collapses and converges, and then it gets out of the loop. And so this actually is exactly what I showed you here. These are the results for that. So if you do this, here's what this iteration procedure looks like. So certainly by iteration 15, you walk out of this loop because you already found the solution. So you certainly don't need to go 100 iterations. So, okay. Now, let's redo this, right? Because all I did before was took these three equations, and for the first one I solved for x, for the second one I solved for y, for the third one I solved for z, and then I made an iteration scheme. So let's do it again. I'm going to take these same equations. So the equations are here, and all I did is flipped the first and the last equations. So the third equation is the first, third equation is the first equation of the third. This is a very simple thing to do. I haven't cheated, I haven't done anything wrong, I just flipped the equations. You would have to agree that the solution still is the same. But now let me make a new iteration procedure. From the first one, I'm going to solve for x, second for y, third from z. Okay? And in doing that, here's my iteration scheme that is different from before, but should have the same solution as before. So what could go wrong? Well, let's go ahead and start iterating now. And here's what happens. I now start to iterate much like I did previously, but before it converged to the solution, but now what's happening is my solutions are going to infinity. And remember when I showed you iteration schemes can converge, but they can also diverge, and this iteration scheme here clearly is diverging. So this thing just blows up, which means it's a horrible method, right? You can't go try to solve ax equal to b and this thing blows up on you, because obviously what you want is a stable method for giving you a solution. And right now we don't know what would allow us to do that, because all I did was switch the first and third equations, and now it doesn't work, and if I had it back the original way, it works. So what is going on here? What's going on here is this concept for iteration, which is called strict diagonal dominance. And this is the definition of strict diagonal dominance. And if you have strict diagonal dominance, then the iteration procedure is guaranteed to converge. And what is strict diagonal dominance? You take the diagonal term at each row. So for each row, go to the diagonal, and you take its absolute value. The absolute value of that diagonal term has to be bigger than the sum of the absolute value of all the other terms in that row. Not bigger than or equal to, greater than. So you go row by row, you look at the diagonal term, take its value, its absolute value, and you ask the question, is it bigger than the rest of the sum of that row? If it is, then you have strict diagonal dominance. And if you have strict diagonal dominance, algorithm is guaranteed to converge. Okay, so let's go and look at it from the two equations that I had written previously. When I had done the first equation, set of equations, here's how they were arranged. So the first equation is up here. On the diagonal is a 4. It's bigger than the sum of the other two terms, which is 2. On the diagonal is 8. It's bigger than the sum of the absolute value of the other two terms, which is 5. And the 5 is bigger than the sum of the other two terms, which is 3. So in the first case, I had strict diagonal dominance, and that's why it converged after 15 iterations. Okay? But when I take the first and last row of this equation and just flip them, now you see where this 2 is? So I have 2 is not bigger than 6, 8 is bigger than 5, and now 1 is not bigger than 5. So this is not strictly diagonal dominant. So this will converge, this will not. So it starts to beg the question, first of all, if I had a matrix A, is there a way to rearrange it to make it strictly diagonal dominant? If there is, then great, you can use this algorithm. You can just switch rows and columns around, switch rows around in order to make it diagonally dominant, and then you can get this iteration procedure to work, and it's guaranteed to work, right? So it's not even a question about might it work, it's guaranteed to converge. But if you can't arrange it and you don't have strict diagonal dominance, then you do not want to use this method. It's not guaranteed that it's going to blow up, but you don't have any guarantee it's going to converge. And so you don't want to start using algorithms that, in fact, don't have guarantees about solving even something so simple as AX equal to B. Okay, let's talk about improvements to the algorithm. How can I make it converge even faster? Remember, I'm giving you a third way. You have Gaussian elimination, LU, now the iterative methods. Now you have 3 ways to solve AX equal to B. And here's a fourth way. So those Jacobi iterations. A fourth way is called with Gauss-Seidel. If you remember before, I had an iteration procedure. Here it is. But now I'm going to change it. Notice that the first equation tells me how to update x. Now the second equation I had before with Jacobi iterations, this is 4x of k. But presumably x of k plus 1 is a better approximation to x than x of k. In other words, if I'm converging to the solution, x of k plus 1 is better than x of k. So I'm going to use it immediately in my algorithm. So I just computing an improvement. So instead of x of k here, I use x of k plus 1, which gives me y of k plus 1. And in the third, I'm using the new improved values of x and y immediately in my algorithm. This is called Gauss-Seidel. So what's going to happen here, we're going to get an acceleration in the convergence time. So notice here, remember took about 19 iterations to get it down to numerical precision. Here it only takes half that, 10. So I can solve this AX equal to B in half the amount of time, which is always what you want to be doing, right? Everything here is about speed. How quickly can you solve these problems? And so really computational speed matters quite a bit. So again, all of this is highlighting different methods for AX equal to B, and I just showed you a new method for solving AX equal to B, which is based upon iteration. Now the important thing here is the way this would work with the iteration is you have to ask the question is how fast can I solve it with iteration? And for very large scale systems, some of these iteration techniques beat the order n squared of an LU decomposition. And this is why people like them, is because they can be faster in some cases, especially for large scale systems that come from physics-based models where you have a lot of diagonal structure in your matrices. Then these iteration techniques can actually be a big improvement in speed, and so you would use them in those frameworks. And we'll talk more about those as we proceed along to more advanced topics here, but that gives you another way to solve AX equal to B.